Totally my bad.
Okay. So I was starting to answer something before I stepped out, but so let's assume. So it seems pretty clear this assignment was rough.
Yeah.
Did you say brutal? It was brutal. All right. So, So once we finish going, maybe I'll find. Well, hold on, just so I can try to adjust the level of insults. Have we already done the hard part, or is the hard part coming?
We did the
I
hard
think
part.
we just did the hard part.
Oh, okay. Oh! All right. I'm back. I realize this was incredibly difficult. All right, so here's my rationale. First of all, my intention was not necessarily to ruin your lives for a week. Most of you who've had me before realize I do get enjoyment out of that. But it was not my intention. My intention is probably for a graduate course with a 1-week assignment for you to spend probably somewhere in the ballpark of 8 hours.
I spent 20 hours on this.
Okay, so I did homework for the next 3 weeks. Because
Is that
I get it. So I'm articulating the situation here from an and then I will try to adjust for this next assignment given the state of things. So watch, the next assignment is going to make 5 times harder. I'm like, you questioned me.
Drop that while you can.
I don't want you to drop
Is
that.
that just programming, or is that including the chapters and the Bible homework and all that?
Well, Bible homework, that's not counting Bible homework. So I would say the programming. The reading stuff, that should be relatively low stress type of.
Well,
I guess, yeah.
It can take a while.
I guess I'm thinking.
That reading takes a long time.
I guess I'm thinking 8 hours of. I probably am talking about the programming stuff because it's the real critical thinking, grappling, suffering, where
I'm trying to figure out how much effort should be put into the reading and how much effort should be put into the programming.
The program is the part that's graded.
Well, I don't.
The reading helps though.
Well, the reading would be a requisite for doing the homework, given that you implemented things from the reading.
Yeah.
But let me try to put this in context, and then we can. But I mean, first of all, you can't just throw a number on something because it's going to really depend on the student. So if I'm going to re-articulate that, let's say I'm saying 8 hours for let's call it the average student in this class should be. Not what the average student in the class is, but what the average student in this class should be. Okay. Now, having said that, my assessment is that the average student in this class is probably in the ballpark of where the average student in this class should be. Therefore, if we went way, 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 way above 8 hours, then it probably was too much in terms of the combination of the assembly stuff with the new language. Having said that, let's pretend it was only 8 hours, because even 8 hours is going to sound like that's still a lot of homework, right? Here's the rationale for something like this. And maybe some of you were so overwhelmed from the assignment that you were in this situation today, but let's assume that you hadn't done any of this homework. Let's assume you didn't have the assignment. So let's go on the extreme. You come to class and I sit here for the first hour or whatever and just write the stuff that we wrote, right? Some of you might be engaged, like, oh, well, I'm a good student. I'm going to sit here and pay attention and all this stuff. And that's all fine and good. But if you had actually gone through the experience of struggling with it and hating it and not getting it and not getting it and not getting it and throwing your laptop and not getting it and all that stuff, when you start seeing the solution come together, that's when learning actually is occurring. Because you're actually seeing, like, oh, that's what I missed. I spent 4 hours on that, and oh my gosh, it was for 4 hours I stared at that. That's learning. if you just had to read the book, let's say, outside of the obvious enjoyment I get from Human Misery, if you had just had to read the book and you spent whatever 2-3 hours, I don't know how long does it take to do the chapter of the book. Longer than 2 or 3 hours?
Yeah.
It's a long.
I feel
You don't realize.
Really?
Uh-huh.
Well, give me a number. How long was the reading? 5 hours?
4 or 5 hours.
Yeah. 3-4 hours.
I'm getting all sorts of numbers there. There was
It
like,
depends on how fast you read too, though. Like,
on average, I should still be getting a relatively, you know.
First chapter was like 7 hours, second chapter 5 hours. It was a little short this time.
If you really are saying we have to complete all the questions there,
Right.
yeah, it probably will take that much of time.
So is 5 hours fair?
If you say finishing the exercise.
Yeah, with all the extra, because I want that. I mean,
That will be.
so this goes back, you know, for your freshman year as an undergrad. In order to solve a problem, you have to understand the problem,
Yeah.
right? And so the purpose of that chapter was to help you understand the problem you were being asked to solve for your homework, right? And those interactive exercises are pretty important to that to make sure you understood it, right? So, so we're going to say it's 5 hours there. So then I would have expected. So let's say, so you take 5 hours, you spread it across, let's just kind of, I'm going to try to put myself in the shoes of a student.
Usually too big.
Well, so, now is this a bad time to tell you I've never done Mips programming before? And this is where Maddie then chimes in, well, it's you, right? Isn't that your thing? That's, but it's you or something like that.
She has a point.
Well,
You've done this before. Maybe not with Scheme.
no, never done Mips.
You've done He's this. done
100% never done Mips.
We have done this. I've been.
No, we've done ARM programming.
Not Mips.
I'm
It's very
scared.
simple.
I've never done Mips. But it doesn't matter. And actually, it doesn't matter for the right reason. The right reason is that computer architecture, what this course is actually about, and for the couple of you who had the ARM class, you realize it's the same thing. Two completely different architectures from completely different generations. Mips has been out forever. Okay? You could find textbooks from like the 1980s that probably had Mips architecture in it. Whereas the ARM architecture, that's what we find, that's like what's in this. You know, this is ARM, and it's the same thing. So computer architecture is computer architecture. You just understand, like, oh, this is what the registers are called. This is what this is how data memory is accessed, and this is what the functions that we're writing are. Okay, but so put that to aside. If I put myself in the student's shoes, and we think about now, I'm going to put myself in a grad student's shoes, though. Which doesn't mean that you're a superhero, but it does mean that there is a higher level of expectation. If it's 5 hours of reading, and I have class on Thursday nights, obviously you're not going to go home after class and start reading. So I probably do half the reading on Friday, and then I'm just telling you how I would approach it. Okay, so I would probably do half the reading on Friday, and I would do half the reading on Saturday.
That's 4 hours.
I thought that's 5 hours.
Half the reading?
You said the reading was 5 hours.
I'm thinking 2 hours, sorry.
Yeah, well, it doesn't matter. I would basically have the reading knocked out by Saturday, so that I have Sunday through Wednesday to complete the assignment. I mean, keep in mind, it is a 6 credit hour course. So I mean, this is like a sixth of a grad degree is in one class. I get it; it's a little compressed, but the alternative is you don't get to be a working professional and all this other stuff. It's not the most ideal way of learning. It just is what it is. The good news is, for those of you who've had me before, my MO is typically for you to feel somewhat challenged, probably, on homework assignments, but then you typically, as long as you go through the effort and do the work and submit it on time. Didn't you turn a couple things in late this week? But typically when you do your part you end up with a substantially better grade than your ego says you should be getting. Is that a fairly accurate statement? You know, when you come out, like, okay, well, what I just turned in is worth a F minus. And it was indicative of 27 hours of my life. All right, and that's why I have the self-assessment. So you can say, look, I just spent 27 hours of my life, and I could have shredded a piece of paper, scanned it, uploaded the image, and it would have been more correct. I always like the self-assessments when you could tell when the student turned it in, they were hot. Just yelling at me and all stuff. That almost always gets some extra credit too. I find that hilarious.
When they get mad?
Huh?
When they get mad? What do you mean by
I go.
Well, like you could tell that they were extremely frustrated in their assessment. The really good ones are when they and I say good from an actual academic perspective, is when you can tell that they were so frustrated with themselves that they just couldn't get it. It just, like, I threw my life into this and it just didn't happen, and I'm ticked off at myself. I'm ticked off at you because you gave me something I couldn't do, and just whatever. But you could just tell that they were mad they didn't get it, right? But then when we come to class and you see it get solved, that's when hopefully the rest of that education takes place. Because that's when you see that, oh, had I just done that, that would have made this, and this so much easier. So now we go back to the whole thing of me putting myself in the shoes of a student. I would have the reading knocked out by Saturday, so I would be able to start working on the assignment Saturday, Sunday, Monday, Tuesday, Wednesday. Plenty of time to run into possible walls where you can then start asking classmates questions, asking me questions, things like that. For this assignment, only a couple of people asked me questions on Slack, and I'm pretty sure I looked at the timestamps. I think I replied back pretty quick, certainly within a reasonable amount of time.
Pretty quick.
So you either need to start earlier so you have more time to hit the wall so you can ask questions, or ask better questions, or I usually encourage people, I realize for working professionals it is harder to do the whole study group thing, but with Zoom and stuff like that, it's probably possible. But take your time management into your own hands and give yourself as much time to struggle with the hard part as you can. Don't wait until the day before the actual programming assignment's due to finally wrap up the reading. Like, okay, well, I finished my 5 hours of reading at my leisure, and now I have 11 hours to do this assignment that I don't even know how to start. That puts you at a disadvantage right from the get-go, right? Okay. Regardless of what your week was like, I get it. Real life gets in the way. We have all this other crap that pops up, stuff that you knew was coming, stuff that you didn't know was coming. I get it. It's real life, and that's the way it is. So you threw as much time as you could throw at an assignment at it. You come up, you come into class. All I really, 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 really want from you, frankly, I don't even care if you get the right answer. I'm going to give you the right answer in class. And chances are, even if you got the right answer, the approach I take, it will be somewhat different than the approach you took. So hopefully you're going to learn from that anyways. But I definitely want you to have spent time grappling with the problem, significant time. We're not talking about phoning it in for 15 minutes. I mean, I want you to really struggle with it, but you're all adults. You can say, look, this is a rough week. I'm at 6 hours. I'm tapped out. That's where it's at. I'm not proud of it, but that's it. But you've struggled with it for the 6 hours. Now when you come to class, you at least have, a foundation that I can now teach on top of, right? Because when I start doing this stuff and you start seeing, oh, that's what that was. Even if we start getting to parts of it, like I just didn't even start that, so I don't even know what he's talking about now, so I'll just watch the videos later or whatever. At least there's a foundation. I could sit up here all day long and I'm, just write this stuff for my health, and it's not going to get you anything. Because at some point you're just going to check out, right? It's like, okay, well, here's another lambda statement, whatever the heck that is, right? You had to have been working on that specific problem to understand what the challenges were of that specific problem. That make sense? All right, so we can all agree that the assignment wasn't as hard as it should have been, and I should make the next one 3 times harder?
I have a question.
Remember, I have to temper this because you've told me the hard part's over. So I don't even know what the rest of the assignment is yet. You're going to have to tell me what I asked you to do.
It's an architecture class, but I really found like we're struggling with, people are struggling with programming. That's weird.
No, it's not weird. That's the problem with our current undergraduate education system. We have people with computer science backgrounds who are coming to school getting master's degrees who don't know how to program.
That's a little ridiculous.
Yeah, it is well, but it's not even the student's fault.
Yeah.
It is how our system teaches computer programming. So I guess I get to be the executioner, and so you're going to get plenty of programming experience. But what I said last time is true. The reason I specifically pick Scheme in here, typically master's programs are viewed as being more theoretical. Okay, so if you're in our undergrad program, you really only use Scheme in one class, and that is our theory class, computer programming theory. Here is how languages are built. So master's programs are typically more theoretical to begin with. Given that, Scheme is a nice tool because of its simplicity, right?
Simple.
I know it's frustrating. Actually, the thing that's most frustrating about it is the fact that it's a functional language. It's just so different than what you've mostly been used to. Okay, but there's several people in this room who've had this language before. Okay, so they don't really have that excuse. The point is that it's still a different way of thinking. It's not like they worked with Scheme a week ago. They worked with Scheme 2 years ago or 3 years ago or whatever it was, and since then they've put a whole bunch of object-oriented procedural programming on top of the functional programming that is long lost in the rearview mirror. It's way back there. And that's okay, because the focus shouldn't be on the programming. I want the focus to be, you have your hands so tied when you're working with Scheme. All you can do is get the first element of a list, or get the next element of the list, or get the rest of the list. You could almost do nothing with Scheme. So you're trying to accomplish something that just seems really complex in practice, implementing the functions of a computer processor. But hopefully when you went through the reading, you realize that computer processors are really simple. There's not a whole lot to them. It's move stuff from here to here. Move stuff from here to here. Do a little mathy stuff, right? That's what processors do. So Scheme is really the perfect complement. The language itself doesn't do very much. The processor itself doesn't do very much. And then it's extra frustrating. We're I'm trying to do nothing with nothing, and it's not working. And I have nothing. All right, so you should be frustrated. I want you to throw as much time as you can at these things. But frankly, if you start, unless, like I said, if you're where the average student should be in this class, and each of you is capable of assessing yourself and deciding, okay, am I about what a student in this class should be? Am I ahead of the curve? Am I behind the, not where I should be? If you're not where you should be, well, that 8 hours is going to scale, right? It's going to be more than that because you're at a disadvantage, and that's okay. But you're also all adults. A lot of you are working full-time jobs. Hey, if you get to hour 10 or hour 8 or whatever your limit is for that week and you're just done, write down your self-assessment. I'm not going to shoot you over it. We're all going to do what we're going to do. And at the end of 16 weeks, the hope is that we've learned something as a group, right? And you get a grade that is indicative of how well you've mastered the material, let's say, ish, because you've gone through this experience. And that's going to make you better in the workforce later, even though it made you miserable in a small time period. Make sense? All right. So now that we've done the easy part of the assignment, tell me what the next one. Go ahead.
So are we going to have
Well, I don't know. What's this week we will. What's the next chapter in the?
The answer's yes.
There's a real high chance in my classes you'll have programming assignments, but like in the research class, we don't do any programming. That's just a lot of writing.
Mips 2 is next.
Mips 2?
Yeah,
Part 2. Mips assembly part 2.
Oh yeah, so it's just harder MIPS instructions. But from what I'm From what I'm gathering from you, if the hard part of the assignment is what we've already solved, it wasn't the MIPS instructions that were hard. It was manipulating lists and scheme,
Yeah.
right? But now if we go back to the record and I look at Slack, I see a question about set bang once that I answered, and I see 0 questions on there about, hey, can you give me an example of how can I manipulate a variable from another function or something like that? Had those questions been asked, I could have real quickly just given you a little example. I wouldn't have solved the exact problem, but I would have given you a code-based example of solving something that maybe would have made your life easier.
Well, I mean, like,
Just gotta ask the question.
Let's go back to the very beginning of lecture where you were talking about creating a whole bunch of little pieces to
Yeah.
solve a big problem.
Yep.
I think, and I might be just speaking for myself, that we might have jumped the gun and tried to solve a big problem, at least at the very beginning,
Okay.
all at once. And so we're like, set bang, let's go. Show us how that works, because that probably is what solves the problem. So, like, manipulating that kind of stuff, like, we didn't get to that.
That didn't feel like it was the hard.
Right.
Okay, so I gotcha. So we came to class today, and the very first thing I dove into was the tools that we were going to need to solve the problem.
Mm-hmm.
The first thing you dove into is the problem and never got to the tools you were going to need to solve the problem.
Right.
And then you just got stuck. You hit a wall.
Right.
Interesting.
At least that's
Yeah,
what
it's fair
happened
enough.
to me.
So then the follow-up to that would be this. If you are working on the assignment and you have hit a wall, you need to tell me about your wall so I can hopefully get you past the wall. Just give you a hint and say, hey, maybe you should think about writing a function that just solves this one problem. You know, something like that. You know, this goes back to the whole thing of how I would have approached it, where get the reading knocked out. It's not fun, but it's part of the process, whatever. And the Xi books are actually really good books. And then, yeah, hey, I mean, yeah.
It's a waste
It
of
would,
money.
it would be nice if, well, you can print it off afterwards, I suppose. It would be nice, though, if you've had previously subscribed to a book, if they somehow gave you access to it.
Sell it or anything.
For $75, you think you can it.
Yeah, but I mean, really what you're paying for is the interactive exercises, which are really valuable, I
And
think.
there should be a txt.txt version then too. If you're paying for the interactive part, you
Yeah.
should be able to get the paper part.
Yeah, I get what you're saying. Yeah, I can ask them.
Pen and paper girl.
Yeah, I am. You want to
Yeah.
see how many notebooks I have?
Well, you know, there actually might be something like that. I think there might be somewhere where you can like export the thing in like a printable format or
I
something.
thought I saw somewhere where it said print this chapter, but no,
Yeah.
I can't find it.
Yeah, there is something like that where you would lose the interactive exercises. Yeah, here, like print chapter.
What does that look like?
Oh yeah, so it's
I usually done too.
And then you could just save it as a PDF. So maybe not super convenient, let's say, but
My brain must
Yeah.
have just been fried after those 5 hours of reading. I'm just like,
out of curiosity, when did you finish your 5 hours of reading? This morning. Back off. No, it was a come at me, bro. Is that No, that's not. It's not. Can't come at me, bro. It's come at me, bro.
I know.
You see, you're gonna mess. I'm learning these things. You're gonna mess me up.
What's the point? Can't be good at everything.
I'm not. I'm barely good at anything. I just happen to be good at some of this stuff.
At least he's on my list.
The highlight of this will make it even worse.
Oh, no.
The highlight. The highlight of my day today was like because we had some pretty intense meetings earlier today. It's like, well, at least I get to come to my grad class tonight and write some scheme Mips code. I was looking forward to it.
By the way, is it relaxed compared with the conference?
This? Oh yeah, this is relaxing.
I
Compared
think
to
it's
what?
relaxing for you.
Yeah, this is equivalent to Netflix.
This is like a getaway?
It is. Isn't that messed up?
Yes.
It makes you hyper.
I'm like planning vacations and
Yeah, I can't even
He's like, I'm gonna see
Well, you know, like when I go on cruises, like several of you know, I go on a lot of cruises with my wife, and we like completely different things. Legit, I go and sit at the wine bar and write software. I'm broken.
Awful.
He's not.
Yeah, but when you hear it out loud, it's different. I mean, I do that. When I'm not eating, I am drinking wine and coding on a cruise.
The life.
I know. It's fun for me.
Yes.
I sit on the couch and watch Netflix and write software.
Okay, but the real question is, like, how do your eyes handle that? Because I can't do it these days. So
They don't. You've seen me go blind in the middle of a class. I can't.
I
there's
want
no
that.
hope for us.
I can't see anything.
That should be another class. You should add a class in undergrad, just like being able to see.
What does it mean to
Once
be a
you graduate
programmer?
and move on
What
to
is
like
the best
programming every day.
posture?
Yeah, because I feel. I mean,
Sitting and seeing.
I've been so used to not being able to see clearly on the screen for so many years now. Because I mean, I wore trifocals before, and then for VR, I switched to contacts, and they're a lot more comfortable. But I can't see anywhere near as well out of them. Distance, I can, but up close, everything's blurry. But I really feel like, based on the percentage of things I see on the screen, I don't know if I need my vision to code. I think if I had somebody there just to tell me what was on the screen, I could probably just say what to write. I just need, because eventually I already have the tremor, so I got to I can't do the space bar with this thumb because this bounces too much.
Blindfold. Let's do the rest of the lecture like this.
Oh, then,
Ready, get up there.
well,
Me? Why?
Yeah.
well, that's fine. We can make that work.
Yeah, I would like.
Hey, but if you're going to test me, then I'm going to test you in the next assignment. Because I know I'm going to pass the test.
Always
I'd like to see it. I think it'd be interesting.
No, I would get all frustrated with her because she wouldn't type fast enough. Like, come on, keep up.
Wait, why am I typing?
Like, that's what she said.
You
Oh, I
know.
thought you wanted me to just go up there and blindfold.
No.
See, now we know why these homework assignments didn't get solved.
You understood what I said. Never mind.
Maddie sits down, just goes ninja mode. Time to do homework. Can't see. Doesn't make a difference. I wasn't going to solve it anyway.
Is that not what you're saying?
No, she was saying they would blindfold me so that the few things I actually can see, I could no longer see. And then I would tell you what to type.
And then you would type.
That couldn't be that hard.
I agree. That's why I was confident I could solve that problem. Probably the problem would have been I wouldn't have been able to understand what you were telling me was on the screen through all the giggles and stuff.
We have to watch Make Toast.
That's right.
Oh yeah.
We made it through lecture. We never have to watch.
All right, hold on. Let me just pause this. And we're back. We're not in any better mood. We just laughed for like 5 minutes, 10 minutes.
We're a little bit better.
Huh? Just a little bit better? Okay. So then somebody tell me what is the next thing we were doing for our homework
We
assignment.
haven't finished the load and store.
Well, we haven't started the load and store, so that's what we're doing is load and store. Okay. And what is the
Well,
syntax?
technically, we did start with that. We did tell you that was the first thing.
All right, hold on. So this. So LW is load word. So what's the syntax for this guy? So we load from memory into a register, right? So LW would be LW, then our destination, and then our source register. So you probably just took in 2 parameters.
They actually pass it in as the memory address. Is the second thing.
This is a memory address?
Yeah.
Okay, so and it has to be because that's how loads work. So we are loading into this register the contents of this memory address. Right? Okay. Huh? This one was easy?
No.
Oh, are you asking me if it's easy?
No, she was kidding. She said easy peasy.
Oh, easy peasy peasy. All right, so we're going to define LW to be a lambda that's going to take in a reg name and a mem location. So those two parameters, right? Mm-hmm. And then what are we going to do? We are going to set reg value, reg name equal to get DM value mem location.
So that's equal to? Hold on, you said equal to? No, never mind.
That should be load, right?
Yeah, okay. Yeah.
So we're loading into this register the contents of this memory location. So what are we going to do? We're going to set the register value, the function we wrote to begin with. What register? This register. What are we setting it equal to? Whatever the value of data memory is for this memory location. Not too bad. Assuming we had those other pieces. Because those other pieces made this one kind of easy, right? Yeah.
Can you try run it?
Sure. So we're going to say what? LW, what's the name of a register? Like T1? And
5008.
yeah, let's make this guy like a 7, just so we can test it. So 500.
4.
All right, and we'll print out our,
Register.
we'll do it before and after, and should see the value get loaded in there. So where's our, where we put it? T1, yeah, there's our 7. And the void thing, this is because the set bang boils down to nothing. So that's why you get the a void output there. So that function doesn't have a result. All right, so that's the load. Store. This is going to be a lambda that takes in a mem location and a reg name.
The memory location is still passed in as the second one.
Yes.
For others.
Oh, whatever, that's fine. So you want it like that? All right, so we're going to store into this memory location the value of this reg name. That's what it's accomplishing. Yeah, whatever order is fine. So we're going to,
Set DM value.
let me just steal this and then I'll hopefully spell everything right. Set
DM value.
equal to, this is mem location. Equal to get reg value, reg name. That should be SW. Okay. And here we'll do SW 5008. Oh, we're doing we'll just do T1 again. 5008, and should have made these better names that I could remember. You know, like not like the exact names that are in the book.
So should we set T1 to a different value then?
Well, we don't have to. I'm storing the value of T1.
Well, they're both set to 0 right now, that's why.
No, T1 is, I'm loading into T1 whatever's in 504. Then I'm storing into 508 which was there. Well, then I could do load T1 from 5,000 to 0 it out. So we should have, this should effectively copy from memory address 504 to memory address 508. So here is, yeah, this is 504 and here's 508. All right, so those are our loads and stores. All right, what else are we supposed to do? Who? Add I, okay. Define add I. And this guy takes a lambda, and what are the parameters for add I? Add I is add immediate. So we're going to have a destination register. We're going to have a register, a source register, and then an immediate value.
Yep.
So you have dest reg name, source reg name val. Oh man, I just know I'm going to type in value later on.
Could we just call it immediate?
Who?
Could we just call it immediate since that's what it is?
Would that make you feel better? That. Okay. So we are going to be setting a value in a register. What register are we setting a value in? Destination register. What are we setting the value to? We are setting the value to add get register value of source register name and immediate. So add I takes in the destination, the source, and the immediate, and we're going to set our destination register, set that variable equal to something. What are we going to set it equal to? The addition of the current value of our source register and the immediate value. So is that add I? Okay, what else are we supposed to do?
Add.
All right, and add, instead of it being an immediate, it takes another register, right? So we can steal add I here. There's add. Source reg, we'll call this source reg 1 name. Source reg 2 name.
Just cover that with the-
Like that. So add works differently than add immediate in that both the values we're adding are registers. So we're going to set the value of our destination register equal to the sum of our source register 1, the value that's currently in our source register 1, and the value that's currently in our source register 2. So that's add. We want to test these, or are we just going to assume they work?
Test them.
It should.
I'm still waiting for my first bug. I have lots of spelling errors, but hold on. What do I do here? All right. So we will let this load into 7 into T1. So we won't do this here. So let's do an add I T2 T1 15. So that should store inside of we don't even need to do the store here. Let's just keep it simple. So we'll load that, what was it, a 7? Load a 7 into T1, because that's what we stored in 504. Then we'll add, storing the result in T2, the current value of T1, which is a 7, and a 15. So it should give me a 22 in T2. And then we'll say add T3. Let's do T1, T2. 29. Because this will be a 22 plus a 7. All right. And then we'll just print out our register, what do I call it, register file. So there's our 22, there's our 29. All right. What else?
Subtract.
Subtract and multiply.
Okay, and subtract works on 2 registers, not immediates, right? So subtract is going to be like add. And we do need to make sure we get it right for which guy we're subtracting from which guy. So we look at subtract. Is it
Subtract the second one from the first.
so register name will be equal to this guy minus this guy? Okay. So set destination register equal to minus this dude. So it should be right just like that. And then you said multiply. Multiply is the same thing. Both registers. Is it what, MUL?
Yeah.
Okay. What else?
That's it.
Oh. That was underwhelming. Really? I thought you were lying. I was hoping you were lying. All right. Is there more stuff in the chapter, though? Don't we have jumps and
In
branches?
chapter 2?
Chapter 1.
Yeah.
Chapter one.
Well, that was stuff from chapter
Oh, yeah, chapter 2. The chapter for this week.
There was.
Isn't there conditional and unconditional branches?
There was the branch for equal, branch for non-equal, and then there was the jump.
Okay. And so let's talk about those guys, and then let's implement those guys. Nailed it. Oh yeah, my pictures. I like
Oh,
pictures.
and there was also the set on less than instruction.
Set on less than. Oh, what? That's a Boolean, so it flips 0 and 1.
Yeah.
Sets it to a 1 if it's less than and 0 otherwise.
Yeah.
Okay. All right. So we want to put this in. So we talked last time about the CPU being this kind of collection of magic tricks that is what our high-level programs ultimately compile down to, right? So if we know that our high-level programs, the way I've taught programming is this idea of that, hey, we have to remember stuff, store things, right? Variables. We have to be able to ask questions, and we have to be able to do repetition. So the two things, right now we know how to store stuff, don't we? Right now I can take something from memory, put it into a register, take something from a register, store it back into memory. So I'm kind of accomplished the concept of storing things at this point. But we haven't really accomplished the concept of asking questions yet. Usually we're asking questions based on some sort of mathematical truth or something like that. So most languages have these things called branches. So it's probably called a conditional branch. Was that what the book calls it? Conditional and unconditional or non-conditional branches. So a conditional branch, this is generic computer architecture, Mips has it, ARM has it, whoever has it. So a conditional branch says if Boolean expression go to a label later in the code. Something like that. Okay, so you are conditionally jumping to that label. So keep in mind, so here are a couple of truths. Let's go back here and let me write this. Let's just write assembly code is a file filled with sequential calls to CPU magic tricks. All right, now that part's important because the natural behavior of a CPU, we have this thing called like a program counter and stuff like that, where the CPU basically, if the CPU is working on a program, so this is kind of where your hardware maps to the operating system because there's a dude who's scheduling. So are you in 350 right now? So you guys haven't probably started talking about CPU scheduler yet, but when you start talking about the CPU scheduler, you have this piece of software from Mac OS or Windows or Linux, whatever, that is in charge of telling the CPU what to work on next. And the thing that your CPU works on next is always going to be the next assembly instruction from whatever program is currently getting CPU time. The way to wrap your mind around this initially is we pretend like we're in one of these old school computers where there's only one program running at a time and it's the only program we care about. So we don't have to worry about all the CPU management stuff with CPUs with multiple cores and things like that, where your operating system is taking one program off the CPU, putting another program onto the CPU, so that us as the stupid users are convinced that our computer is doing everything simultaneously. No, we're in an old computer where our CPU does one thing at a time, and its only job is to run a single program, so we don't have to think about that side of things. What does that program look like? It looks like a file filled with sequential calls to CPU magic tricks. Instruction, 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 instruction. Now, each line is either, and this is going to be kind of a half-truth, but I think it'll be the easiest way to describe this. Each line is either an instruction or a label. We can say this is a place, a branch. Let's call this the destination of a branch. All right, most assembly languages will allow you to put the instruction on the same line as the label. I suspect Mips is probably the same way, but doesn't matter. The point is we have a collection of two things. We either have an instruction to be executed, or there's a label that may or may not have an instruction right next to it, or it might just be on the next line. But that label is the destination of where a branch might go. Okay, so it allows us to like skip over things, or skip past things, or go back up in your code, right? So if you do, if you branch from down here back up into your code, what are we emulating there? Do this, do this, do this, do this. Ask a question, branch back up. Do this, do this, do this, do this. Ask a question, branch back up.
Wow.
It's a loop. That's how you implement loops. Body of the loop, jump back to the beginning. How do you, and you have two different kinds of loops. We have pre-check loops, we have post-check loops, right? If it's a pre-check loop, we're going to ask the question before we do the body. And then what do we do if we're not happy with it? If it's a pre-check and we fail, we just jump past it to the label that is following the loop. Continue on. If we're going to execute the body at least once, we go ahead and do it. We have our our branch instruction here. It's a conditional branch. If it says we should do that again, we jump back up to another label. So understand here, a label in and of itself doesn't say to do anything special. So the code next to or associated with the label would execute. Let's see if I can give you some sample of that in the book. I'm sure it's there. Has everything I said so far pretty much map up to what Mips is? Branch. What are these guys? Just give me some sample code. Okay, yeah, so here's some sample code. So BNE, this is going to branch if not equal. Okay, so we're going to check the contents of T0 and the contents of T1. If these guys are not equivalent to each other, we will branch to this label called CONT, continue. So what does that mean? It will mean skip this line and jump down to this line and hit it. Okay? Now, let's assume, for this example, I don't know what the values of this are up there, so just follow me in just this example here with me giving you some values. So let's say T0 is a 5 and T1 is a 6. Is it true that 5 is not equal to 6? That's a true statement. So we will branch to continue, and what we will do is we will add an immediate to whatever's in T2. So we'll add 2 to whatever's in T2. We will not have executed this line with a 5 and a 6 in T0, T1. But let's say T0 and T1 are both 5. If they're both 5, this is what happens. Is it true that 5 is not equal to 5? That is false. That is not true that they're not equal to each other. So we will not branch to this continue. So what's the natural behavior of an assembly program? Go to the next line. So we execute this right here. Now that's not a branch instruction, right? We do some math. So we do that. What's the natural move of an assembly program? Next line. So now we're on a line that happens to have a label on it. This label marks the destination of a branch, but we didn't get here by that branch. We just naturally stumbled upon this line, right? So this guy doesn't mean anything to us in and of itself. We just go ahead and do our mathy stuff for it and move on with life. Does that make sense? Okay, so we go through an assembly program linearly. Every now and then, let's say, it's actually pretty common, but there'll be branches that jump us to different places, potentially, right? And those labels give us those destination landing zones, okay? But you can bump into a label without any branch just by hitting that line naturally. If you want a line to be skipped under another circumstance, like kind of like an else, you can use a jump. It's an unconditional branch, which will then jump past a line. So I can like put another, maybe called a label called after or something like that. And maybe on this line here, I do a jump to after. And it goes ahead and just splits past it. So if I say branch if not equals, if it's not equal to it, it does this guy. If it is equal to it, it does this, and then maybe jumps past CONT as an unconditional. All right, so that's how branches work. So we can see how that branch construct allows us to solve the problem of conditionals, if statements, as well as loops, as well as functions. Isn't a function just a collection of chunks of code that's reusable? Mm-hmm. So maybe we have a function that has a label called, I don't know, factorial or something like that. And whenever you want to do factorial, you jump to that label called factorial. It does the logic for it, and then jumps back to where you left off in your program. That's why we keep track of this thing called an instruction pointer, an IP, for your on the CPU to pick up where you left off if you leave to go and call a function or something like that. All right, so these are the constructs of our high-level programming languages, and we're seeing how they're all implemented in these very primitive things in our low-level languages, just through these things called branches. All right, so in order to really test this stuff, we need to be able to have a collection of instructions, right? Now, how would you, if we're dealing with scheme here, how would you represent a collection of Mips instructions? It's a list of instructions, right? Down here, we have 3 instructions. I'm going to load something, I'm going to add an immediate, and then I'm going to add. If we were to imagine this as our assembly program, that's what it looks like. So we'll say define my program, LOL. So I'm going to leave it like this for right now. We don't quote this because these are actual things. Okay? Now, we will need to think about how we go about doing this. So let's think about this from processing a assembly program. So we have this program called myprog, and myprog, and I'm going to organize this a little bit here. All right, so that's my program. Kind of gives us our, if I do this, will it kick it all the way to the left? Yeah. It's a nicely formatted function, right? Ha. All right, so this is my program. Here's my assembly instructions. I want to be able to feed this guy to the CPU and have the CPU walk through this, executing each instruction. And the default behavior is for it to go one line at a time. We haven't implemented this idea of jumps or branches or anything like that, right? All right. All right, so let's define, I don't know, the CPU to be a lambda that takes in a program. And this guy is going to go through every element of that thing and execute an instruction. So we're going to say if null, because programs are lists of instructions. That's what we decided our program is. That's what our slide here says. It's a program is a file filled with a sequential calls to CPU magic tricks. So a program is a list of instructions. So if I'm out of stuff in my list, then we can just say we're done. So really, we only want to ever do something here if we're not out of stuff in our list. So if not null prog, so if I still have stuff in there, I want to go ahead and execute that instruction and then move on to the next instruction. Okay? Kind of have to cons it to fake this. Let me leave it as the null for right now. We'll build a list. All right, so after each instruction, we want to when we're done, let's go ahead and show the contents of our of the register in memory, maybe something like that. So we'll go ahead and we'll just do a list of register, what's it called? Register file?
Yep.
And data memory. So I'll just create a list out of those two. That just gives us a dump of our two things. So if I'm done executing my program, we're just going to say here's the final state of registers in memory. Otherwise, what do I want to do? I'm going to, let me just actually close this real quick. I'll come back and edit it in a second. So we're going to say define execute instruction. And this guy's going to be a lambda that takes in an instruction. And for right now, we're just going to have them call that instruction because we actually have it done in function calls. But we're going to change this in a few minutes. All right, so we'll just say, okay, what we'll do is just boil down to instruction. That's what execute instruction does. So for example, this guy is an instruction. So if I pass that and say execute that, we might need to apply it. We'll see. But it's not the way we're going to end up doing it anyways. But we're saying just do that. Whatever that is, do it. Okay? So that's what execute instruction does. Let me go ahead and steal this. And I'm actually going to call this guy the Mipsy. Is that how it is? Mipsy CPU? Okay, we'll call it that because that's what it's going to be an implementation of. So I'll list the final things when I'm done executing all my instructions. Otherwise, I will go ahead and I'm going to create a begin statement. This might be handy for some of the things that you're trying to do. It's effectively a block statement in a scheme where I could say I want to do this, this, and this, 3 things in a row. It's not overly handy. It'll just, otherwise I can just cons the result here. But I wanted to do several things. So what I wanted to do is I wanted to execute the instruction. What instruction? The car of prog. That's the instruction I want to execute. And then what do I want to do? Then I want to go ahead and call Mipsy CPU. Huh?
It does have an S after the P.
Which one?
Mips.
Mip. S after Mipsy, like that?
Yeah.
Really? There's an S and a Z?
Yeah.
I don't like that.
Thought you wanted to know.
All right, so coder. What?
What's the program?
Prog, yeah.
Why are you getting the coder?
Because I just executed the first instruction. I want to call Mipsy CPU on the rest of the instructions, so the very next one. All right, so that would be like our Mipsy CPU. I could actually map execute instruction across my list of instructions, but that's going to totally disqualify me for any branching. We're kind of starting to go towards the idea of branching here in a second, but an assembly program is a list of instructions, right? So I need to go from this instruction to this instruction to this instruction. Let's start with doing that naturally, right? But then we're going to do that in terms of how a CPU actually works, where we do have branches and things like that. So this is kind of like a have-z solution just to make it work. So because right now execute instruction just literally takes in a full-fledged executable instruction, because that's what these guys are, right? That guy right there in and of itself is an instruction. That guy works as is. I don't have to do anything special. So all I'm doing is I'm passing that to execute instruction and then just telling him it's that. Just do that. All right, so if I go ahead and then we'll go ahead and say Mipsy CPU, and we'll give it the name of my program, my prog. Why is it complaining? Oh yeah, I'm gonna have to do the apply. That's fine. We're not doing this way anyways. It's not letting me execute the instruction directly like that. Okay, so what I'm gonna do is I'm actually going to change my program a little bit. We know that these are the function calls, but I'm gonna change these guys to be symbols. I intend to do an LW on these two parameters. That's what I'm saying here. All right. So, and then I'm going to put together the instruction here. So under execute instruction, we'll take something in that looks like this. So this is a list whose car says LW. It's not a function LW. The car says LW. That's telling me this is what I want you to do. I want you to load a word. And then we say, well, what does load word take? Load word takes two parameters. The car of the cooter and the car of the cooter. All right. So we'll have a cond in here. We'll say car of instruction if this guy is equal to LW. That's what I'm currently looking at. What do? I will call LW on the car of the cooter of instruction along with the car of the cooter of instruction. So for LW, if this is the car, I'm going to call my normal LW function that we wrote a little bit ago, passing it the car of the cooter and the car of the cooter. Those two parameters. That's if I'm looking at an LW. Else, if I'm looking at an SW, what parameters does SW take? Same order, right? So we'll call SW car of the cooter and the car of the cooter. Takes two parameters. All right, then we have an add. So add, we'll call add, and add takes, what, three parameters? A destination, a source 1, and a source 2. So we'll call the car of the cooter, the car of the cooter, and the car of the cooter. That's right.
Just laughing.
Isn't that fun?
It kind of reminds me of what we did in undergrad with our own programming language.
It should remind you exactly of that, because CPUs work the same way. CPUs do the heavy lifting for programming languages. Why would a high-level interpreter work really any differently than our processors do? It should more than remind you of it. And this is giving you a good preview. It's like, I'm just screwed. Hey, this is what happens when you try to squeeze some electives. He'll get over it. At least I'll find it funny.
Are you going to do intermediate as well?
Yeah. I'll do as many things as you guys tell me I should do. Because I don't.
We don't tell you to do it.
Well, then it's still going to be due, because just like this stuff, like, well, it was in your comments, but you didn't put it on. What is this, like your first? For some of you have an excuse. This is your first rodeo with a Littman class, but for you, it's like fairly common practice that I give an assignment in class and then forget to put it on Blackboard.
And I told you to put it on Blackboard.
And I did put it on Blackboard.
I know.
She's just saying I didn't put the equivalent up
I
there.
mean, there's instances where you've given like a completely different homework assignment in class and then completely something different on like say Monday. You'll post something on Blackboard that's like,
Yeah.
what?
And you should always do what I meant for you to do.
The one in class or the one you post on Blackboard?
Whichever one's harder.
How we know which is harder?
He's saying
You should do both of them and then decide.
Until we go for the 10 hours and we say, oh, this is slightly harder.
Basically, Littman class needs to be a full-time job in itself.
You people are messing up my vacation here. It's like they should make the movies. Isn't there a movie like the Nutty Professor, the Crazy Professor, or something like that? They should like do a remake. I should be in it.
It should be called. It can't be called the Nutty Professor.
No, I think that's what it's called.
Well, no, your movie.
Yeah, but they keep doing remakes of like. I mean, didn't they?
What they did, yeah, a remake, like.
Yeah, but they call it the same name. It's like the modern version of like the same movie. Like how many Spider-Mans do we have now? Yeah. Like, well, how many like Spider-Man origin stories do we have now? 3, yeah. So it's like the Tobey Maguire one. I don't think counts. What's funny is it seems like most people like the current Spider-Man, the Amazing Spider-Man one, the best. I like the middle one with it was mostly technology based, where he was kind of hacking the stuff in his rooms. I just thought that was more interesting, but. Probably the movies are better, the newer ones.
Did you hear about the huge controversy between Sony and Disney?
Yeah, Isn't Spider-Man's leaving the Marvel universe or something, right? Because of
so Sony owns Spider-Man, right? And Disney's like hopping on board, and they're like, you can be part of the Marvel universe. We want like, I think it was something really small, 10% of profit.
Yeah.
And so Homecoming and Far From Home come out and they're a huge hit, and now Disney's like, hey, we want 50% instead. We changed our mind. So he's like, heck no. Like, we're not about that.
It'll change.
And then Disney's dropped them. And so now, Tom Holland has like 2 more movies or 3 more movies with Spider-Man. He's just got 5 total. And now they can't reference any of the Avengers in the upcoming movies.
What?
As of right this second.
It is tragic.
I bet you that the next movie does reference the Avengers.
They based off the second movie all on Iron Man's glasses.
I know.
That was the entire movie.
Yeah, you're worrying about something that's just media gossip. These are all things that checks fix.
Checks.
They will they will come to an agreement and decide, you know what, 1% of a ton is a lot. so we will take the deal.
Disney terms?
Huh?
Disney terms?
It'll all work out.
They're like one of the biggest companies I've ever that run.
Well, all of them are big. Sony's a big company too, but
Disney's being greedy. You could just knock it off.
remove Disney, insert company you've heard of's name
Right.
is being greedy.
That's true.
It's just
Disney has a lot.
well, but I mean, really. So this kind of goes maybe to like almost an ethics type of thing, where it's almost to be expected. It has nothing to do with. It's almost like the old adage, the money is the root of all evil, type thing, because it does change not just people but companies, and I mean, this is something we've been dealing with a lot at Concordia. And I've been here since '06, and the way this place has changed since 2006 is drastic. But one thing that is impressive is if you look at Concordia as just a normal plain Jane business, just pretend like it's a company, Apple or something like that, the school should be substantially farther off mission than it is now if it was a normal company. So when you look at it through that lens, you say, hey, Concordia is actually doing pretty well given its success it's had over the last 15, 16, 17 years. But at the same time, you can then look at it through the other lens and say, you know what? It's under pressure from society and its own success and all these other things where it's maybe hard to hold on to the Christian mission of the university just because of the nature of the problem it's solving in the world around us. And that's with a place that's trying to do the right thing. Regardless of whether you like Administrator X, Y, or Z at Concordia or something, as a whole, I think Concordia is trying to stay on mission. You got a company like Disney or something like that. I don't know about the specifics of an individual company, but I'm sure there's plenty of companies where they're not necessarily trying to do the right thing or something like that behind the scenes. So imagine how bad that could get. So money will solve this problem. So you will have your, what's his name, Tom Holland?
He's the Avengers in the movie.
Yeah. Well, I know the guy was the actor's name, the Amazing Spider-Man actor. All right, so add I.
Multiply, subtract.
All right, so add I has to call add I. So if we're equal to add I, we're going to call add I, passing it the destination,
Exactly.
the source, and the immediate.
Yeah.
Okay.
Does it error with 3 Ds? Question mark.
Who?
Does it error out with 3 Ds?
I don't think so.
No.
For CADDR?
You?
No, I think it's like 7 or 8.
You sure?
Yeah, you can have a lot.
Yeah. But it's not infinite. I think it's like...
I tried 3 A's and it errored out.
Well, it didn't error out because of the 3 A's. It errored out because you didn't take something that was carable.
Yeah.
That's the correct pronunciation, by the way. I use the Old Dutch, but it's the...
I have a question. Is this repetitious?
Huh?
Is this too repetitious?
What do you mean?
Like, is there a way that we can just not always call out the same thing most of the time?
Well, not for instructions that take the exact same number of parameters. But we will have instructions that take a different number of parameters. Just these happen to all kind of do the same stuff, so they take the same number of parameters. But at least they're easy to write. So we have sub.
Modular.
And then we have MUL.
Yep.
Anything else?
That's what we have.
All right, so there's our execute instruction. So then our program, we updated. In fact, actually, I'm going to just drag the program farther down to where our CPU is so we can look at the code a little closer. Or I probably did. Yep, looks like it. So we pass the CPU our program. It's going to go through there. At the end, it's just going to give us a dump of the register file and the data memory as a list. Otherwise, we're going to execute our instruction. Which instruction? The car of our program, which is a list whose first value, a list whose car is the symbol for the instruction we're calling. Okay, not actually a lambda. And it will go through and say, which symbol did you give me? If you gave me an LW, what will I do? I will call my normal LW function on the correct parameters. Okay? And it'll go through and do that for this guy and this guy and this guy.
Will it break if the command is not exist?
Go in my program. Oh. No, it wants it quoted like that. All questions resulted as false.
Do you need to take now that it's
So it is.
now that it's all
Yeah.
Yeah, you don't need that. Otherwise, you have to take another form.
Yeah, so now we can write the code cleaner because it's got to be a bunch of quoted lists. By quoting it up front here, it says don't try to execute that stuff.
One last.
Yeah. All right. What should this have done? This should have loaded into T1, whatever's in 504, which was a 7. I think we had a 7 there. Then it should have added a 15 to that, so giving us a 22, storing it in T2. Then it should have put in T3 a 29. So here's the T2 is 22, here's the T3 is 29, and here's the T1 is 7. So there's the result at the end of that. All right, so that's executing our code now. All right, so now we can run Mips assembly programs on here. So the next thing we want to do is we want to be able to put in branch instructions and jump instructions. All right, so let's take a 12-minute Come back at 9 and do our final hour. Sound good? All right. And we'll get those things put in there.